All right, everyone, welcome. Today, we are going to kind of get into another major topic that by itself is not bad. We're just going to add it into accumulation and curve sketching and all that stuff. So it's just another level to it. But once we have this one under our belt, we can then begin to do some of the more interesting FRQs built around curve sketching. Typically, I will give you a derivative graph, and you'll use this thing we're doing today to answer a lot of questions. So this is just adding to it. Not too bad by itself. Like I said, the end goal today is not that bad, and it's not bad if we just keep putting it with everything we have. But like I said, it's building pretty fast. So let's back up a little bit. The first thing we began with were our indefinite integrals. An indefinite integral was how I began this whole thing with you guys. And it looked like this, and it was something like 2x dx. And I introduced integrals like this to you purely as a means of saying, look, this symbol meant antiderivative. And when you took the antiderivative of the inside, it was derivative in reverse. And we found that this was the answer. So an indefinite integral solution, when you evaluate it, is another equation, basically. Then we talked about definite integrals, where I kind of threw bounds on our little symbol for integral from like 1 to 3. Oops. And this said, okay, do the same thing. Find the antiderivative of 2x, which is x squared, but evaluate it from 3 to 1. And I just told you to plug in top bound minus bottom bound. So 9 minus 1 is 8. Cool. Then I linked this idea of the definite integral to something called accumulation, or area under the curve, which is the same idea. When you accumulate the area under a curve, you get back information about the original function. So when you accumulate like under a derivative graph, you find out kind of like displacement in the original function. If you accumulate under a normal function, you just get area. It doesn't really used in terms of like physics or motion or anything. But then last class, we found that if you divide by the interval length, you get an average value. So that's one time you would accumulate or take a definite integral of an actual function that's not a rate. Most of the time, we are accumulating a rate. So this function right here, most of the time, will be the rate. It'll be the derivative function. Okay, so now we're going to introduce a new idea. It's called a function defined by an integral. And here's how it works. We're going to say we have a function where we'll use the notation g a lot. And we'll say g is the integral of some other function. We'll call it f for today. And the bounds will be some bound. The bound on the bottom will usually be given, and we'll talk more about that as we go through this, why this is usually given. And the top bound is the variable. Now, we are going to add, this is one of the most confusing parts of this whole thing. And I think it makes a lot more sense when I get into Desmos a little bit. The variable in this problem is x. That's the variable. That's what we're going to substitute in for. When I start doing examples, this will become a lot clearer. So this idea is going to feel a little weird until you start seeing me do examples. We can't use x inside the integral because we're already using it as our variable on the bound. So we use something called a dummy variable, another variable. Typically it's t, to just work as a placeholder when we start doing these calculations. So you're going to see how this works, trust me. And I think this idea of this dummy variable will make sense. The point is, if you put an x here and out here, it wouldn't make sense. X is the variable in the problem. T is going to work itself out fairly quickly, and you'll see how that works in a second. So just stay with me on this. the notation you're going to see a lot of times will be g of x equals the integral from some numerical value on the bottom, x the variable on top, and we'll have an internal function. Okay. Let me show you some of the basic stuff today. We're not going to run too crazy with this idea. More, I need you to be able to handle these specific things. So check this out. Here's a pretty typical example. It'll usually say, given, they'll give you the accumulation function, g of x, equals the integral from 1 to x, f of t, dt, where, and then they'll give you the f function. They'll say where f of t equals 2t. Find, we'll find a couple. We'll do what we did a second ago, g of 2, g of, let's do another one, 2, 4. So, look what really is happening. I gave you a function called g, and I'm asking you to evaluate it at 2 and 4. That's no different than a lot of the stuff we've done this year. I give you a function, and I ask you to evaluate it by plugging in the value. It's really all we're doing today. The difference is the value we're plugging into is that happens to be the bound of the integral. So, give myself a little bit more room. So how would we evaluate g of 2? Plug 2 into the function in the variable spot. Well, x is the variable, so it's 1 to 2 of our f function, and the f function is right here. I could have easily put it right here, but there's a reason typically we keep them separate, which we'll get into later. And now you're back to doing a problem we did earlier. So by hand, you could do this one. Take the antiderivative and evaluate it from 2 to 1. So 4 minus 1 is 3. Plugging top down minus bottom. So look what happened. We have plugged in a value 2. We got out a value 3. It's just a function. It's just a little bit different because the function's input is in the bound now. Now, do you see what I mean by dummy variable? The variable t was present here, but as soon as we took the antiderivative and then plugged in, that variable went away. T was not a factor in this problem. The t variable was just kind of like a placeholder. It allowed us to do the internal calculation, but it never really, it didn't matter. I could have literally made it any variable. I could have named it k or l or anything, but it's typically t. So why is this technically a function? Well, I'll get a different output for a different input. So if I plugged 4 into this, it would be the accumulation or antiderivative or definite integral or whatever you want to call it, from 1 to 4 of 2t dt, which is t squared. Again, that's nothing different, but 4 to 1. And that would be 15. So this is just a new way of thinking about a new type of function. It's a function defined by an integral. It's an integral in the middle of this function. So a helpful thing to kind of see, the cool thing about this is Desmos can handle these. Your graphing calculator cannot. So let me do this. I'll put it down here. Yeah. So again, look what I typed in. I gave you g of x from, oops, this should be 1. From 1 to x, and then I told you what f of t is, and I can get all kinds of values. Watch this. I can get our g of 2 value. What's 3? Didn't we have that? We did. And I can get our g of 4 value. So Desmos can handle these types of accumulation functions. That's another name for it. It's an accumulation function or a function defined by an integral. These are going to start to play a major role when we get into the newer FRQs. But before we move on and do, I mean, that's basically it. But before we move on, something else I will ask you to do. These ones are more basic, where we're doing kind of something we're used to. On the flip side, what if I ask you to do this? Find g prime of x. All right, so stay with me on this because there's going to be a shortcut once I do it, but it's worth kind of doing the long way. So how do you find the derivative of an integrally, of a function defined by an integral? Let's see if we can kind of put the pieces together. Ready? So we have our function. G of x is equal to the accumulation from 2 to x of f of t, which I'll just plug back in. So we're still working with the last example. Well, we're going to keep it as x this time. And we're going to go through the problem treating the bound as x still. So watch. I'm going to take the antiderivative with the bounds x and 2. I am going to plug in the top bound minus plug in the bottom bound, which is x squared minus 4. And then I'm going to answer the question. What's the derivative? We'll just take the derivative of that. So what do you notice kind of is going on in this problem? And I'll make it really clear on the next one. If I start with this accumulation function or function defined by an integral, and I ask you to take the derivative of it, it's almost like there's a massive shortcut where I could have just plugged the bound in, the top bound, and have been done with it. And this is something we're allowed to do this, which we'll see again. I'll really make it clear. This is called the second fundamental theorem of calculus. Oops. It says that if you take the derivative of an integral equation like this, or a function defined by an integral, you literally just cancel the two and you are left with what happens when you plug the top bound in, for the most part. There's something else going on too, which we're going to flush out in a minute. But that's kind of the major idea going on with, taking the derivative of an accumulation function. And then you could use it to find, for example, the derivative of like 5, let's say. Then you just plug 5 in and get 10. So bringing Desmos back into this, let's see if Desmos can recognize this. G prime of x should get you the same thing as the original. See that? Oops. And yeah, the derivative should equal f. I mean, at the end of the day, you're taking an integral or an antiderivative, and then you're taking the derivative of it. You should get back to where you started. So that means, like I said earlier, if I ask you to find g prime of 5, that should literally be the same as f of 5, which is 10. Okay. So that was a lot. I'm going to show you exactly what I mean on this next example. We're going to go through all of the different things I need you to be able to do leading into where we're going. So let's do another example. So I will give you a function defined by an integral or an accumulation function. I'll say g of x equals the accumulation from 5 to x of f of t dt. And I'll give you the f function. Now, why am I doing this separate? Why am I not just plugging this function in right here? Because, as we've already seen, sometimes we have the equation, but more often we're not going to have the equation. We're going to have the table or the graph. That's when this really becomes useful. So a lot of times this will not be an equation. A lot of times what we'll have right here will be a graph or a table. So we'll have an accumulation function and we'll have a table or a graph. But for today, we're not going to have that. Today we have an equation. Today we have equations, which makes it relatively easy to kind of go through. All right, so let's come up with another one. What about 3t squared plus 2t? All right, let's do these three problems. Well, two. Let's find g of 7. Let's find g of 5. Let's find g prime of x. And let's find g prime of 1. Sure. Okay. Even though 1 is less than 5, doesn't matter. This 5, as we'll see, has an important property down the road. All right, so first things first, g of 7. This says to find g of 7, what's the accumulation from 5 to 7 of the f function. And then we can do the math. And at this point, you can either do it by hand or do it in Desmos. So this one I gave was relatively not too bad. We can just do it by hand. The antiderivative, don't forget to take the antiderivative, is t cubed plus t squared, evaluated from 7 to 5. Plug in 7, you get 7 cubed. 49 times 7 is 340 something. I don't know. 7 cubed, 249, 343. Sorry. 343 plus 49 minus, plug in 5, you get 125 plus 25, which is 343 plus 49 minus 125 minus 20. Oh, my calculator just died. Uh-oh. I'm using decimals too much. 242. Real quick, we can see that Desmos did the same thing, I'm sure. So again, we'll come back, have an accumulation function. This time it's a 5. 3t squared plus 2t, g of 7. Let Desmos be your guide as you are learning how to do this. Okay? All right, so then what about g of 5? To find g of 5, same deal. Plug 5 in for your bound. And same word. Oops, I should have put the function. 3t squared plus 2t. All right. Antiderivative is, again, t cubed plus t squared, evaluated from 5 to 5. Plug it in. You get, well, 125 plus 25. And I'm hoping you've already seen this. You're going to get the same thing. What happens when you add and subtract the same thing? You get 0. Oh my gosh, that's an important fact. When the bounds are equivalent, you get 0. Why? Well, if I take the area under the curve and there's no area because it's on top of itself, the start point and the end point, there's no area. It's just 0. So anytime the bounds are the same, you're going to get a 0 value. So just kind of keep that in mind, which is another thing that we'll see later. So spoiler alert, it's kind of like this bottom value is giving you the initial condition. It's telling you g of the bottom bound equals 0. It's giving you the initial condition where the function itself equals 0. That's how that's going to factor in a little bit. You don't need to know that right now. Again, just go through the calculation. Okay, g prime of x. So again, I'm going to do it one more time where I do the long method, and then I'm going to show you the shortcut again. And then we'll do that last one. G prime of x. Well, let's start with g of x. G of x is the integral from 5 to x of 3t squared plus 2t dt. So first things first, let's take the antiderivative. T cubed plus t squared from x to 5. Plug in the bounds. X cubed plus x squared minus 125 plus 25. Or x cubed plus x squared minus 150. That's the g function. We unpacked it basically and found the original. Well, we want the derivative of it. So really, when you take the derivative, what happens? You get 3x squared plus 2x, and the minus 150 goes away. And look where we started, or where we got, right where we originally were. So again, the shortcut, when I ask you to find g prime of x, the shortcut is just take the bound and plug it in. I always get the question, so it's worth going back and watching this again. What about the bottom bound? Why does it not matter that I'm not doing anything with the bottom bound when I'm doing this shortcut? Well, look, when you take the antiderivative and you get this number here, as soon as you take the derivative of it, it goes away. So the bottom bound doesn't factor in when you're taking the derivative of an accumulation function. Just like the initial condition doesn't matter when you have the derivative. It's only when you have the original function that it matters. There's a lot there. Again, just kind of be careful with the calculation. And then finally, g prime, what did I ask? 1. It's just 3 plus 2, which is 5. And we can see that Desmos can probably confirm this for us. g prime of 1 is 5. And again, that has nothing to do, it does not matter what this bottom bound is. Watch. That value is not going to change even if I change this value. Because, like I said, if I take the derivative, sorry, if I take the antiderivative and then I take the derivative, the constant term goes away. And you're left with just the variable portion of it. You may want to go back and think that through a little bit. There's a lot going on there. I get it. Okay, so let me do 2 more kind of examples with you. This is a lot, actually. I didn't realize what was here. Why do we have to deal with this stuff if I can just keep finding antiderivatives? Like, what's the point? So what's the point? Here's an example that kind of shows the point. If I give you this accumulation function, something like e to the t squared. It's always a classic example. And I ask you to do things like find g of 3 and g prime of x and g prime of 3. Okay, well, you can't take the antiderivative of this. You can sit there and try. You don't have methods to do that. We don't have a method for finding and nor should you. We're not going to find the antiderivative of this. So as soon as you get to this point where you plug 3 in, you can't do this by hand. You're just going to use Desmos. So in other words, why is being able to talk about an integral, or sorry, why is it important to be able to talk about a function this way? Because if I want to talk about the antiderivative function of e to the x squared, no, it likes f. What the heck? One sec. F of t equals g of t. No, it doesn't like that. Interesting. What if I put it right here? Sorry, one sec. It doesn't like what I'm doing. There you go. Yeah, whatever. Here. Subscripts cannot be empty. Oh, I think it doesn't like this. Sorry, technical error real quick. There we go. Okay. Well, it really didn't like that. Weird. Desmos is freaking out a little bit. But here's the point. I don't know what's wrong with my Desmos. Trust me, it works most of the time. There's no way to express this using antiderivative notation that we know. But by defining g of x as the antiderivative of this, I can now find that actual equation, even though it's not expressible by normal conventions. So let me say that again. I can't find the antiderivative of e to the t squared. But what I can do is talk about the integral by creating a function defined by the integral. So that's one way to deal with it. And then I can do all the stuff I want to do, like I can find g of 3. It's some super small number. Because the bottom bound is 5, I gotta change that to 1. There we go. The problem with this, Desmos, is gonna struggle a little bit with these. Because like I said, your graphing calculator will not handle these. We have to do all these by hand. You'll see what I mean when I say we'll do these by hand later. But a lot of times Desmos can handle these, which is cool, but it just kind of chugs along a little bit. So this value is 1,443. Okay, so let's use that awesome sweet shortcut. G prime of x is equal to, just plug this bound in, and you get ex squared. So in other words, which I'll show you on the last example, if I define g of x as an integral function with f of t as the internal function, the derivative of that is just f with x plugged into it. That's the big connection I'm trying to make. So if I take the derivative of both sides, the derivative and antiderivative symbol cancel each other out, and you're left with just f with the x function plugged in. And then finally, g prime of 3 just means plug 3 in. It would be e to the 9. All right, one more. And I'm just going to give you the shortcut because I'm kind of low on time. I might talk more about this later. Last one, because I do give you one of these on your homework. If I give you this function, sure, of 2t dt. Stay with me. I know it's been a while, 25 minutes in. And I ask you to find, most of the time, I'm going to ask you to find g prime of, like, let's say 3. All right. We know from the last one that if I take the derivative of this, the derivative and antiderivative cancel, and you basically just plug the top bound in. Completely true. But there's something else going on that you got to remember. And I'm going to tell you right now, and if you're curious and seeing why it works the way it does, I'll show it to you in a second. But here's what you need for the homework. You need to multiply by something. It's kind of like the chain rule. You have to multiply by the derivative of the bound. So in other words, it would be 2 times x squared times the derivative of the box, 2x. And that's how you find the derivative of an integral, of a function defined by an integral when the bound's not just x. So this is something, it doesn't come up a lot at all. This is pretty rare, but this is when the bound is something other than x, is a function other than x. Okay, that's enough to do the homework. I will show you why if you're curious, but other than that, I mean, you can go watch or go do the homework, but here's why. Think about if I did this like we've been doing it. So I start with g of x equals the bound from 3 to x squared, 2t dt. Take the antiderivative, which is t squared, from x squared to 3. Plug in the top bound minus the bottom bound. So that would be x squared plugged in, squared, minus, plug in 3, you get 9. And then take the derivative. Like, I mean, yes, we could simplify it. So sure, it's x to the, I think it's easier not to simplify it so you can see what's going on. And now take the derivative. Well, it's a chain rule, right? The derivative is 2 box times the derivative of the box. So 2x squared times 2x, which is exactly what I got up here. So often we'll use the shortcut. You just got to remember to multiply by the derivative of the bound. Okay. So that one was kind of long. I didn't realize that was going to be so long, but that's okay. Purpose is this. I guess it's because I did a lot of intro here. We're going to start having functions where we're going to define them using an integral. The bound on the integral is the variable. T is the dummy variable because when you actually do the calculation, it doesn't factor in. The real variable in the problem is x. It's just kind of what happens when you take the antiderivative and then you plug in your bounds. A lot of times we will just do this with Desmos, or we'll have a graph and we'll just have to know what the link is between the two. All right, we're going to build on this. So do the homework, make sure you can do the calculations, and we will define, or we'll talk more about this as we go. All right.